Hello and welcome. My name is Nick Brimley, and I'm the director of the Slag Cement Association. I will be moderating today's webinar, Practical Implementation of Internally Cured Slag Cement Concrete Using Superabsorbent Polymers. Our speaker today is Chibueze Ajuonuma. He is a PhD student in the Lyle School of Civil and Construction Engineering at Purdue University. His research focuses on evaluating the performance of innovative concrete mixes in real-world applications, with particular emphasis on internally cured slag cement concrete, which offers a sustainable, durable, and eco-friendly alternative to conventional cementitious materials for modern infrastructure. He is also an SCA research winner for our 2024 Slag Cement Sustainable Concrete Awards. If you have any questions during the webinar, we ask all attendees to please use the Q&A feature, and we'll get to your questions at the end. And with that, I will hand it off to you. Thank you.
My name is Jan Olek. I just wanted to briefly introduce Chibueze. He's our student here in the School of Civil Engineering at Purdue University, and he worked with me and Kendra Erk, who is a professor in the School of Material Science, on a demonstration project that was sponsored by the Indiana Department of Transportation to explore the role of internal curing in cementitious mixes containing slag cement for concrete bridge deck applications. The project included field trials to evaluate the feasibility of dispersing superabsorbent polymers during production in a commercial ready-mix concrete plant. And the aim was to see whether it's feasible to do it under the field conditions and what kind of improvement in the properties can potentially be achieved using the combination of slag cement and superabsorbent polymers. So without further ado, I will turn it over to Chibueze so we can share a bit more about his work.
Okay, thank you very much, Professor Olek, and most especially thank you, Nick, for organizing this webinar, and that connected and made our time to connect to this webinar. We truly appreciate you. I'll be sharing my screen shortly. Yeah, Nick, can you see my screen?
We see you are sharing your screen, but yeah, we see your slides now.
Okay, just
Oh, Chibueze, you may want to have it in presentation mode.
yeah, just a minute.
Okay.
Oh, just. Yeah, can you see my screen now?
Yes, we can see your screen.
Oh, okay. Thank you very much. Like Professor Olek rightly mentioned, the research is a practical implementation of internally cured slag cement concrete using superabsorbent polymers. And just a quick overview of some of the outline we'll be discussing this afternoon, depending on where you're watching from. We'll look at the research overview, where we'll look at some of the goals, the experimental overview, the methodology, and materials and mix design. And then we delve into the results and discussion. Under the results, we look at some fresh properties, where we consider the slump, the air content, and then some strength characteristics. We look at the flexural, the tensile strength, and the compressive strength. And most especially, we look at the durability performance of the concrete specimens, where we consider the scaling resistance, the chloride ion penetration, rate of water absorption, as well as the resistivity and formation factor. We know that there's a growing demand for sustainable construction, and is driving innovative solutions, which is aimed at enhancing both the durability and service life of concrete structures. And one of those can be attained by improving the quality of the microstructure of concrete. And we can curing. And further that superabsorbent polymer, which is known as SAP, is also comes handy as one of such innovative materials or innovative solutions, which tends to create reservoirs within the concrete that helps to provide additional water, additional moisture, within the cementitious matrix that improves the hydration of concrete. And we found out that for the internal curing, it relies on the controlled release of water within the concrete mixes. This helps to improve hydration, reduces and mitigates the self-desiccation in concrete structures. All these are geared towards producing a more durable concrete, because we found out that the durable concrete, it helps to, first of all, reduce the maintenance cost, of concrete infrastructures. It helps to increase the rate or the return on investment of concrete infrastructures, the bridge decks, and so forth, and then also decreases the frequency of replacement of these structures. Most especially, we talk about the decrease in carbon emission and energy consumption. Just a brief overview of what superabsorbent polymers is, because not for my audience, we found out that superabsorbent polymers, they are majorly known as hydrogels. They are cross-link polymers. They have a capacity of absorbing moisture, water, in large volumes of water compared to their own weight, and then they end up forming insoluble gels. They are predominantly used in hygiene products such as Pampers, and for agricultural purposes, where they are used to moisture the soil. They absorb, they tend to absorb excessive water from the soil, and then during the period of drought, they tend to give it out to the soil. But we are trying to incorporate this material into concrete because we found out that it can serve, it will be beneficial for internal curing. It can serve as an internal water reservoir for concrete, and also can be an alternative to using the use of pre-wetted aggregates, which is very most times difficult to in the mix design, and then also some of the benefits we've talked about: improved hydration, we've talked about the reduction in moisture gradients, and then we'll also talk about it mitigates some of the durability challenges in cementitious systems, such as drying and autogenous shrinkage, such as scaling resistance. It helps to minimize near surface drying of the concrete, and most especially improves the quality of the microstructure of the concrete to end up giving a more durable concrete. And from some of our previous work, before we delve into the macro, like the using of superabsorbent polymers for macro projects, we did some previous work in the lab in the micro scale. Well, if you're interested in the study, you can scan the code and see some of the things we found out in the micro scale. We're able to find the absorption capacity of the superabsorbent polymers in cementitious mortars, the effect of whether extra water is needed or extra kind of superabsorbent polymers, how we can incorporate it into the concrete for effectiveness. And some of our outputs that we're able to generate from there is that we saw that there was a comparable and improved mechanical properties of the cementitious mixtures. Also, there was a reduction in autogenous shrinkage, which is key. And then we also found improved hydration, as well as improved durability of the cementitious mixtures. But we, beyond what we did before, for this project in view, the goal of this project is to determine how the delivery method, and mixture composition can influence the internal curing performance of concrete formation. Concrete having a commercial SAP formation the new type 1L cement, and some supplementary cementitious materials like slag, and also the addition of colloidal nanosilica. And the research objective for this project, we'll try to evaluate the internal curing performance of the commercial SAP in this concrete mix, and most especially also develop and evaluate the practical strategies to implement, successfully deliver SAP in concrete, especially for real-world application. And finally, we were able to, the objective was to conduct a field trial, to evaluate the strength, the durability, performance of the mixtures, for those cured with commercial curing compound and those cured using superabsorbent polymers. I also want to emphasize on this. One of the study in terms of the objective 2, in terms of effective way to deliver SAP in concrete, there's a way, where they try to add SAP in for commercial for large scale application. They use repurposable bags, but it was ineffective. As you can see here, at the end of the day, even after mixing 40 plus revolution in a concrete mixer, they found out that there was still dry SAP there, and then also the bag did not dissolve. So we, in order to able to solve this problem, we're able to develop, we're able to, propose a practical way whereby we use the dissolvable bags, the SAPs we are repackaged using dissolvable bags, and the SAP, we found out that approximately 1 pound of dry SAP, can be used for 1 cubic yard of concrete, and then this at a rate of 0.2% by the weight of the binder. And this dissolvable bag, we found out that it's for storage purposes, is enclosed. The bag was enclosed in an outer waterproof bag, but which is usually we open it and then add the dissolvable bag directly into the mixer, and it was very much effective. But before we were able to carry out this experiment for the field trial, we tried to do some laboratory experiments, to see the effectiveness of using dissolvable bags. So in the next phase of this talk, the webinar, these are some of our laboratory experiments that we did. These are the conventional concrete mixing materials, where we were able to, the cements, for cement, we use type 1L cement. For slag, we use the slag grade 100, and the concrete, the quartz aggregate, the fine aggregate, the superabsorbent polymers, and the admixtures that we are used for the concrete. For the mix design that we use for the lab scale experiments, we designed 5 concrete mixes at a constant water to cement ratio of 0.44. And we're able to, because we are trying to evaluate how effective the dissolvable bag that we propose or we brought on board, how effective they are in to disperse SAP, and how effective it is for internal curing purposes. So we had the reference mix, and then we had the 2 delivery methods where we added the SAP using the dissolvable bag, and secondly, we directly poured the SAP into the concrete mixture. We did this for the reference mixture where we just added SAP, and then also 30% cement replacement using slag, in which we also added the SAP directly, and then also DB we also kind of added using the dissolvable bag. Our target slump was between 3 to 7 inches, and then the air content was 5 to 8%. And due to the volume of concrete we needed, we had to scale down the bag to a smaller scale because we needed a small quantity of the SAP at 0.7 kilogram per meter cube of concrete. So we scaled down the bag, and some of the results we obtained from the laboratory experiments. Here we had the result for the fresh properties, where we tested the slump and the air contents, and we can find, if you see here, we found out that quite all right, the addition of SAP reduces the slump of the concrete, but we also found out that there was a kind of a comparable result both in air content and the slump, both for the addition of SAP using the dissolvable bag and directly pouring the SAP, showing the effectiveness of addition of SAP using dissolvable bag. And we proceeded with the compressive strength. These are some of the results of the compressive strength that we obtained by the addition of the SAP and directly pouring it or through the dissolvable bag. We can see that there was a steady increase in the compressive strength, because we tested the compressive strength for 3, 7, and 28 days. And then we see a steady increase in the compressive strength with age. And then also we had the comparable results between the addition of SAP using directly and that of the dissolvable bag. The same was with 30% slag replacements or cement replacements using slag. Then we also evaluated the flexural strength at 28 days. We also saw some similar strength parameters, strength increase with age, and also evaluated the ultrasonic pulse velocity to see the homogeneous the homogeneity of the concrete matrix, and this is a range of the results we obtained for the ultrasonic pulse velocity at 3, 7, 14, and 28 days. We saw a steady increase in the pulse velocity with age, and then also we saw a comparable result between directly pouring sap and that of the dissolvable bag. And with this, armed with this result, we proceeded for the field trial C concrete, which requires 658 pounds per cubic yard of cement, and at a constant water to cement ratio of 0.44. Our target concrete slump was between 3 to 7 inches, and our target air content was between 5 to 8%. And I also want to emphasize that there was no super plasticizer was used, no high range water reducer was used for this mix, because we employed the services of a commercial concrete mixing company for this project. And this is a schematic of the slabs we made in the field. We're able to make a 8 feet by 8 feet by 10 inches formwork for the concrete slabs, and then also there was an improvisation for 10-inch by 4-inch diameter digs, which we use for the spacemen we use for the scaling resistance. And just an overview of some of the pictures from the field. The concrete mixers, like I said, we employ the services of a commercial concrete mixing company, and the concrete mixes we are done. And then we tested for the fresh properties, the air content for every of the mixes, the fresh properties, the air content, and the slump was evaluated, and also the concrete surfaces, because we wanted to ensure that we obtain the at most real life application, so we employed the services of professional concrete finishers, and then the slabs we are finished, we are properly finished, and we also I also want to emphasize for curing, we the slab was partitioned, and half of it, was covered with plastic sheets, whereas the other half was we applied the curing compound on the slab. And so an overview of all the slabs after we finish the work, and also beside the slab that we are done in the field, we also cast beams, 12-inch, 6-inch by 6-inch by 18-inch beams for flexural testing, and prismatic specimen, as well as close to 200 numbers of cylinders for compression testing. And also for each of the slabs, before the slabs the concrete for the slabs we are poured, they were instrumented with thermocouples, so that we can be able to evaluate the temperature. The temperature, we are able to evaluate the temperature evaluation, for the concrete mix, over time. And at each of the testing ages, 7, 28, 56, 90, 365 days. Cores we are extracted from all this, from the slabs, and tested and brought into the research laboratory and tested. And I also want to emphasize here for the curing regime, we had 2 different curing regimes for this project. We had some of the specimens that were cast in the field, but we are brought brought back to the laboratory so that we're able to condition them at a constant temperature of 23 degrees Celsius and relative humidity of 50%. And they were also exposed to wet curing. The variability, we had some of the specimens, some of the samples that were cured using the curing compound, and some that were cured without the curing compound, here indicated by NC, and those that were cured with curing compound were indicated by CC. And then we also had some specimens that were cured using addition of colloidal nanosilica, here as indicated by NSI, and then those cured using SAP. And then also we had some field, those were cured in the field. They were the concrete slab they were cured they were cast in the field, and they were left there for a period of 365 days. And then for them, the condition there was a varying temperature, there was moist condition, and the cyclic freezing and thawing. And then also we also had the curing compound and those without the curing compound. And moving on, we proceed to some of the methods we use to extract some of our results. We evaluated the fresh properties here. The specimen we have fresh concrete, where we evaluated the air content and the workability, the compressive strength at 7, 28, 56, 90, and 180 and 365 days. Were also evaluated. Cores were extracted from the field. We evaluated the flexural strength for the beams, and then also splitting tensile strength, as well as scaling resistance and resistivity and depth of chloride ion penetration. Just an overview of the specimens we used for the scaling resistance. The concrete scaling resistance, like you said, is an experiment. It's designed to evaluate the durability of concrete surfaces. That's the ability, to resist scaling when they are subject to cyclic freezing and thawing. So, chloride of kind of de-icing chemicals. So here, such as sodium chloride or calcium chloride. So for the test specimen that we use, we had a 10-inch by 4-inch diameter cylinders, which were extracted from the field after 28 days of casting. And then for some of the specimen that had curing compound on them, where they were power washed to make the surface clean, and they were kept at ambient condition for 23 degrees until testing. Now for after that, we built the dike around them, 2-inch dike around them, and then after that we added the icing compound, which is a calcium chloride at like 0.2 inch of the icing compound, and they were kept, they were exposed to 50 cycles of freezing and thawing. We had freezing at -18 degrees Celsius for 16 hours, and then thawing at 4 degrees for 8 hours. And each of the after 50 cycles, and each of the icing compound was replaced after every fifth cycle, and this was repeated for 50 cycles. Also, for the slabs in the field, they were ponded. They were ponded. We were able to create dikes on the slabs in the field after 28 days of casting, and then they were ponded using 4% of calcium chloride solution, and we maintained it for a period of 150 days. We were able to stimulate, we will try to stimulate the real world application, where real world condition of chloride exposure. So the dikes were carefully covered to avoid contamination and evaporation of the compound. And at the end of 150 days, the surfaces were cleaned and cores were extracted from the diked portion, and they were split, and silver nitrate was sprayed on the surfaces to obtain distinctive profiling. And some also for water absorption experiments, the cores were extracted and cut to the required dimension, and they were vacuum saturated. They were conditioned in the environmental chamber. After that, we were able to evaluate the rate of water absorption. So now that we've introduced the project, we've highlighted some of the goals and the objectives. We've explained some of we've talked about some of the the experiment we did in the field. I will be shifting gears to some of the results we obtained. For that, we'll look at the results we have in the workability, the results with the fresh properties, the strength properties, the durability properties, and finally, we'll do a conclusion. So for the fresh properties, like I've said earlier, the target slump and the target air content was 5 to 8%, and target slump was 3 to 7 inches. And we noticed that the addition of SAP, for the concrete, the mixes, the addition of SAP, reduced the slump value, but all the text lab, all the concrete mixes we did, we are within the design target, the design values, but the addition of SAP reduced the slump. But this can be improved by the addition of the super plasticizer. But for this project, no super plasticizer was used. But if you want to increase the slump, we can add a high range water reducer. Then these are some of the pictures from the field. The reduction in slump by the addition of SAP. And for flexural strength, the beams were tested at 4 days, because we're trying to evaluate how easy or how fast if this SAP or this was used in the field, how easy can the road be opened to traffic. So we were able to evaluate the flexural strength at 4 days, and the range we had was between 410 to 550 psi, and from the INDOT standard, they said that the minimum modulus of elasticity at rupture for 7 days is at 570 psi, for structural concrete. So we're able to, but we had 550 psi at 4 days. So for compressive strength, like I said, the strength values were evaluated for 7, 28, 56, 90 days, and 365 days. We're able to see that we're able to see a gradual increase in compressive strength with age. We're evaluated now at the left side of the plot on the left side are the concrete strength, the compressive strength of the cast samples that we brought back to the field. Whereas the right side, we are from the cores we extracted from the test lab. We also evaluated them. So we were able, for the result, we found out that the incorporation of admixtures such as nanosilica and slag, it improved the strength properties, especially at later age. We saw a kind of a 14%, 23%, 25 and 30%, as well as 48% increase at 7, 28, 56, 90, and 365 days respectively for the 30% slag replacement. And but for the core samples, we see a kind of a variation in the strength properties. We also noticed that the addition of superabsorbent polymers, into the mix, it improved the hydration of the cementitious matrix, resulting in increase in the mechanical properties such as compressive strength, and these are as a result of internal curing of the SAP particles. Like if you notice the bar from the reference, that's the first set of bars, comparing it with the fifth set of bars, you will see the steady increase in compressive strength at all the curing ages. And most especially, we also noticed that the mixes that had slag and SAP in them, there was also, for instance, the last set of bars, we also noticed a steady increase in compressive strength, with age, showing there's a synergistic effect between with SAP and slag, resulting in improved hydration, and which resulted to increase the compressive strength. So for curing condition, like I explained earlier, we had 4 different curing condition. So we had the reference mix. There are no curing compound was applied. We also have some others that had the curing compound that were applied, which is seen as CC. And then we had some concrete mixes. That's the third set of bars that had the nanosilica, colloidal nanosilica, and then we had the addition of SAP. So we found out when we evaluated this, we found out that the addition, the incorporation of the curing compound, it slightly had an effect on the compressive strength, especially for the mix, for the samples that we brought, we that were left in the field. If the plots on the above were those that were cured in the lab, and the ones below were those that were extracted from the field. So the addition of the curing compound was had a kind of slight effect on the compressive strength. But we also noticed a consistent increase in compressive strength when we compared the reference mix without the curing compound with those with addition of SAP. We had a 54% increase at 7 days. We had 54%. We had a 54% increase. 45%, 40%, 42%, as well as 43% increase at 7, 28, 56, 90, and 365 days, for the mixes that had the SAP in them. And the same trend was also observed for the splitting tensile strength. We noticed a slight decrease with the addition of colloidal nanosilica. The addition of slag. We noticed an increase in the tensile strength, and then the SAP also we noticed an increase, and then also the synergistic effect of the SAP and the slag also resulted in an improved splitting tensile strength. Now, regarding the durability, if we move to the durability performance, these are some of the results we had from the scaling resistance, experiments we carried out, and we're able to we evaluated this using a surface visual, rating scale, which shows severe rating at when it's 5, and then when there's no scaling at when it's 0. So for all the specimens that we evaluated, none of them showed any sign of scaling. There was no mass loss recorded for the 50 cycles, so showing that there was an improved performance of the concrete structures which have a strong resistance to scaling. And for depth of chloride penetration, after the specimens that were extracted and split, we did a profiling, and we found out that the depth of chloride ion penetration was in the range of 1.5 to 2.0 cm, with the reference mix having around 2.5 cm. So using this baseline, we found out that the addition of slag, it greatly reduced the depth of chloride penetration, signifying there's an improvement in the microstructure, showing that also there was it resulted in a denser concrete mix. And then also the slight, if we check the mix with SAP, there was also a reduction. There was also a reduction in the depth of chloride ion penetration. And we also evaluated the water absorption. The same trend that happened in the depth of chloride penetration was also evident in the water absorption, the rate of water absorption. The addition of slag, it helped to reduce the water absorption. This can be beneficial, as it will help to reduce the ingress of water and substances that can be detrimental to the concrete. And finally, we also evaluated the resistivity of the resistivity. We're able to assess the influence of concrete microstructure and durability, especially with respect to the ingress of water, so that we have measured the electrical resistivity. We found out that the electrical resistivity, there's the concrete specimen with a greater volume of interconnected pores, showed lower resistivity, but those with lower volume of interconnected pores, so that the concrete specimen with slag, resulted in higher resistivity, which is also beneficial, which can be beneficial to the concrete infrastructure in terms of durability performance. So, in summary, we found out that having performed this field experiment, first of all, we're able to establish that the use of dissolvable bar was an effective approach to deliver SAP in the field, without it gives appropriate dispersion, and then mixture, as well as mixture consistency. And then also we found out that the SAP also, it improved the early flexural strength, as well as significantly improved the compressive strength, performance of the concrete mixtures when we compare it with SAP-free mixtures, because we had values of between 30 to 50% of strength increase compared to those without SAP. And then also, most especially, we saw that mixtures containing slag and sap, displayed reduced chloride penetration depth, when we compare with the reference mixture and the sap only mixtures. So we find out that the combination of sap and slag, it appears to provide a synergistic effect, together, reducing the permeability and enhancing the resistance, to chloride ion penetration. Most especially, there was also a reduction, the higher resistivity, in mixes containing slag. This shows an improved durability. I want to thank you for your wonderful time, and most especially, I want to thank my research team. Professor Oleg, Professor Ek, she sincerely wanted to be here, but she had a busy schedule. And for every Dr. Raikan, for everyone that helped out during the field trial, and those that have connected here, I want to appreciate you all. Most especially, I want to acknowledge this project is sponsored by the Indiana Department of Transport through the Joint Transport and Research Program. And I want to also appreciate Purdue University, especially Lies Engineering, and most especially, I want to thank Nick and the Slag Cement Association for this opportunity, because we can't be here without you guys. Thank you very much for this opportunity. This is the code for the previous projects we did. We're expecting that the reports of this project will be available before this webinar, but unfortunately, it's not available, but we'll make it publicly known when it's available. Thank you very much.
Thank you, Chibueze. We are now taking questions, so please feel free to enter your questions in the Q&A box, and we'll get to those. But Chibueze, could you speak on maybe some of the biggest challenges you had with your studies, or maybe the biggest surprises that you had, anything like that come to mind?
Yeah, regarding challenges, from the conception, both from the conception to the actualization of the project was challenging, because the project was done at the peak of winter. We started it at September, and then it progressed through the winter, the summer, and so most times, especially during the peak of the winter, going to extract cores from there, was so challenging. It was so challenging, exposed to freezing cold. But beyond that, also there are also other technical challenges that were also in terms of logistics, getting everybody together, trying to work into people's schedule, and it was very difficult, but we were able to pull it through.
Perfect. We do have another question here. The question is, you showed that the particle size of the SAP was less than 300 micrometers. How large was the smallest particles?
For this project, we didn't characterize in this particular project, but from our previous project we did, I think it's between 200 and 300, between 200 and 300 micrometer. Yeah.
Perfect. Oh yeah, everyone, please feel free to enter. We got another question here. Was shrinkage performance assessed between different mixtures? If so, what did the results look like?
Sorry, can you repeat yourself, Nick?
What was that? Say that again.
Yeah, can you repeat yourself? Sorry, I didn't get it.
Yeah. So the question is, was shrinkage performance assessed between different mixtures? If so, what did the results look like?
Yeah, we also evaluated the shrinkage of different mixtures, both with mortar specimen and then concrete. And then, with the mortar specimen, we saw a reduction in drying shrinkage for mixtures that had a sap in them compared to the mixtures without sap. We had a higher shrinkage, for mixture with 30% of slag, but with addition of sap, because we had mixes that had sap and slag in them. The incorporation of sap in them was able to reduce the shrinkage, to a minimum level. So there was a reduction in shrinkage for mixes with sap.
Perfect. See if there's any other questions. If not, if you have any questions later for either of us, please feel free to contact us at Slag Cement, at info@slagcement.org. We can answer your questions directly there. You can contact me at nick.brimley@slagcement.org as well. If you'd like to see this webinar at a later time, we'll have it available on our website, slagcement.org, and it'll be available on our YouTube channel as well. With that, I want to thank Chibueze again for speaking. He did an excellent job. Oh, and we got one more question here. During mechanical processing, how does the particle size affect the absorption capacity and release rate of SAPs?
Nick, please, can you repeat yourself, please?
Oh, sorry, yeah. During mechanical processing, how does particle size affect the absorption capacity and release rate of SAPs?
Well, the particle size, the particle size I know plays a significant role in the absorption, the water absorption for SAP. But for this particular project, we are not there was no emphasis on different SAP type, because we concentrated on one particular size of SAP or type of SAP. So this project, it's beyond the scope of this project, because we didn't evaluate different SAP. So I can't categorically say this performed better or not. But I strongly believe that the particle size will have an effect on both the absorption and the water release of the SAP particles.
Got one more question here. Did you notice any early cracking difference using SAP?
Sorry, did I notice any what?
Yeah, so did you notice any early cracking difference using SAP?
Cracking difference. Okay, we also carried out because of time constraints, I didn't kind of project the study we did on the microstructure of the concrete mixtures. But when we evaluated the microstructure under the microscope, optical microscope, and then SEM, we found out that there was a reduction in the micro cracks, with the SAP, showing the improve the microstructure, the kind of improved hydration, although, there was a kind of, it reduced the air content, which was also what we saw from the fresh properties, but there was also a drastic reduction in micro cracks, in the concrete mixtures. Also, this can help to improve the interfacial transition zone, in the concrete, so improving the durability and then mechanical properties.
So we got one more question here. In concrete applications, what particle size range is considered most effective for internal curing?
For internal curing, that's for SAP particles. Yeah, I know there are different formulation for SAP particles, and personally, I've not worked in details with different SAP size range. At the moment, I'm working with this particular SAP, from SNF which is between 200 and 300, which we use for this project. So I cannot categorically say emphatically what are the effects of different particle size of SAP, what it will have on the different performance characteristics of concrete.
There's no additional questions. I just want to once again thank our speaker today, and I want to thank all of you for attending as well. And as I mentioned earlier, this webinar will be available on demand on the SCA website and our YouTube channel. Thank you so much for attending.
Thank you so much, Nick. Thank you. I truly appreciate you. And thank you for everyone that made out time to connect out of their busy schedule. We truly appreciate you. Thank you.
Thank you.